This meeting is being recorded.
In this video, we're going to take a look at another additional aspect of aqueous equilibria from chapter 17. Here we're going to look at what's called complex ions and complex ion formation, and then their solubilities. So what we see up top here is a new type of K, a new equilibrium constant. This is K sub F. This is called the equilibrium constant of formation. And we're given this when we have a complex ion that forms. So what happens is a metal ion, a cation, which has lost some electrons, can act as a Lewis acid. It is electron deficient. So it can form a complex ion with a Lewis base, which, if you recall from their definition, this is an electron donor, and then this would be an electron recipient. So what we see here are some common complex ions that we may encounter, their Kf values, and to help out, our equilibrium equations are given here in this table as well. So we mentioned that the metal cations can act as Lewis acids. The other portion of our complex ion, besides the central metallic ion, is called a ligand. And these are Lewis bases that I mentioned earlier are going to act as these electron donors. So they need to have at least one lone pair. So we know even ammonia and water, which are neutral, they also have those one or two lone pairs respectively. So they can also act as Lewis bases, and then hydroxide and chloride obviously have plenty of electrons. So these can bond to a metal, form this complex ion, and then we'll see that adding a common ion in these cases can increase solubility. So let's take a look at another example here, an introduction, where we have our our silver chloride, which we should note that that's a slightly soluble salt. We're given a KSP value here, 1.8 to the negative 10th. And we also have our ionization equation. So we're going to, in fact, combine this equilibrium constant and this in an equation and get a new equilibrium constant to tell us the concentration. So what we have here is our dissociation first, and then we have our second equation gives our complex ion formation equilibrium equation. So if we were to multiply our KSP times our KF here, we'll get this new K value of 3.1 times 10 to the negative 3. So we can also note that in this scenario here that changing the pH, specifically lowering it or adding acid, will not increase the solubility because HCl would form. We have that chloride ion. So again, that will be a strong acid, and it will just ionize, and we'll have a left shift, so less solubility of our salt. So let's look at exercise 16 here and see if we can calculate what concentration of free silver, like we did above, will result in an aqueous solution prepared of 0.1 molar silver nitrate and then 3 molar ammonia here. And so we have our combined equations already done here. So we have our silver nitrate, and we're gonna, that's already dissolved. So we only see the silver ions here because that's all that's going to react with our complex ion formation reaction. So we have our silver ions, and we started with 0.01 molar. We have also started with 3.0 molar of our ammonia, and theoretically we'll have none of this complex ion that have formed yet. So all of this silver will get used up. So we're going to subtract here the coefficient of 2 times that same value, the 0.10. So we're going to in fact subtract 0.2 from 3. And over here, we're going to add 0.1. So just like previous ice tables, but now this will be 0. This will be 2.8, and this will be 0.1. So below, we're going to start with our initial concentrations now of silver. We're going to utilize this Kf value. Let's set up our Kf expression. It's still going to be products over reactants, as we've seen in the past for every other equilibrium expression. So there's my product, and here's my reactants. Now, note that the ammonia, we're going to have to square that value. So when we plug in our values here, we'll take special note that we square that value for the ammonia. So we have to get our equilibrium concentrations down here before we can plug them into that equation. So what's my change? As always, we're just going to make a variable plus x here. This is going to be now plus 2x because in this balanced equation, we have 2 ammonia included. And then here we're going to subtract x. So we're going in the opposite direction now. So we want to know how much of this free ion of silver is present. So now we're going in this direction. So our negatives over here on the right, and our positives are on this side of the arrow. So what do I have? So I'm going to have 0.1 minus x over here on my reactant side, and then 2.8 plus 2x here for this product, and then x here. So these are my values that I'm going to plug into this equation over here. So I have 0.1 minus x up top. Then I'm going to have x down here and 2.8 plus 2x. So this value here, this 2x, this is going to be very small. So we're going to ignore that, and we're just going to square this 2.8 here. Because as we've seen in the past, sometimes our changes are very small. In this case, we have a large Kf in our forward direction. So in the reverse direction, we expect a very small Kf in this direction. So that's why we're ignoring that 2x. So let's take a look here. We're going to rearrange our equation, and we're going to set it equal to this Kf value. So let me jump down here below a tiny bit, and we'll squeeze that in here. So my Kf was equal to 1.7 times 10 to the 7th power. I have my 0.1. Oh, I forgot we're going to also just ignore that x there as well, because it's pretty tiny and negligible. And then I have my x that we're not ignoring here, and then times 2.8 squared. So let's make sure that we plug everything in correctly here. We want to solve for x, so I am going to end up rearranging this equation so that my x would be equal to 0.1 divided by 2.8 squared. All right, so that's going to be, well, my x is equal to, I just plug this right into the calculator, and then my x will be equal to 7.5 times 10 to the negative 10th molar. And remember, we were looking for our silver ion concentration.